Okay, so we're here at Southwest Research Institute, which is in San Antonio, Texas. It's a large facility that does lots of science. They have a fire test division that does full-scale testing for the purpose of certifying systems for use in buildings. And so I'm going to have one of the guys out here, David Hintz, show you several of the tests that he works on, that he runs, and give you a little bit of detail about what they look like. We're not going to see the test actually run, but at least you get to see what these things look like up close. Okay, I'll take the camera off you and off you go.
Hey everybody, David here, research engineer. I've been working at Southwest Research Institute for about 5.5 years as a project manager, basically organizing large-scale fire tests, fire resistance tests specifically. And when we talk about fire resistance, we're talking about the passive ability of divisions, or really the ability of materials to passively resist fire as opposed to actively suppress fire like a sprinkler or a water mist system. So we deal a lot with composite materials, foam insulations, fibrous insulations, fiberglass, mineral wool, ceramic fibers, all that type of stuff. So right behind me, I don't know if Dave, you have to take a step back to get this in the shot. This is our large-scale vertical furnace. It's got a 12-foot by 12-foot opening, and what you're seeing here is, well, it's a furnace. It produces fire. On the back wall, we have 9 pre-mixed burners, which, sorry, truck's going by. 9 pre-mixed burners, which mix air and gas, so that if we have conditions inside the furnace which are not favorable for combustion, such as an air deficient environment, we won't lose combustion at the burners because you have your air and your gas necessary for combustion occurring right at the burner. The probes coming through the back face of the furnace are temperature sensors. The ones that are installed in there right now are for the Astm E119 standard. I'm going to get up here and just point at a couple different ones real quick. So this is your standard E119 probe. It's a type K thermocouple that's inside this metal tube is a ceramic insert, a double bore ceramic insert. You have 2 different material wires that go through the 2 bores of the insert. They have a welded junction where the insert terminates, and then the whole assembly is placed inside an Inconel tube. Inconel is a nickel alloy metal. So your measuring junction is actually inside this metal tube, so it's shielded. So you get a slower response on these thermocouples. And then up here, if Dave, you can zoom in on that, this one right here, this is a thermocouple that used to be used by the International Maritime Organization, which is the organization that deals with marine and offshore oil platforms. What you see right here is actually what you would see inside the E119 probe if you took 4 inches off the front. You can see the ceramic insert and then 2 wires coming out that have a welded junction at the front. Because this is not protected by a metal tube, a metal sheathing, if you will, this has a much faster response. It sees the temperatures much quicker than the measuring probe on these do. So the reason we have these 2 different types is these are the thermocouples specified by the fire test standards for controlling the furnace. But since we have a much quicker response on those, it gives us a better indication of what's happening inside the furnace before we see it on the slower response thermocouples. So basically what you would do to run a fire resistance test, I don't know if you want to take a step back here. This is a test frame, and this has a 10-foot by 10-foot opening built into it. So what you would do in one of these fire tests is if you're looking to test a 1-hour rated wall assembly, you would construct that actual assembly into this opening right here. Just for example, a very basic typical construction that you would see in an actual building is a steel stud. Maybe it has fiberglass or mineral wool insulation in the stud cavity. And then on each side of the studs, you would have 5/8 inch thick sheetrock. And so we'd build a wall like that into this opening, and we would put that up against the furnace and hold it in place. And we would burn it for 1 hour. And during these fire resistance tests, you're following a time temperature curve. So at specific times throughout the tests, you're looking to hit specific temperatures. For example, 5 minutes into the test on E119, you're supposed to be at 1300 degrees Fahrenheit. 10 or 15 minutes, somewhere around 1400 degrees, and eventually half hour, you're at 1550, and it gets hotter and hotter as you go along. So, so that's our vertical furnace. We test everything from walls to fire dampers, fire doors, cable penetrations. We do columns inside this furnace. So I'll show you our other furnaces, which are all used for basically the same purpose. It's all about different orientations. So this is for vertically oriented test specimen. And right behind us over here, we have our large horizontal furnace, which has an open top and burners obviously down beneath it. And what you would use this for is testing floor ceiling assemblies, or also cable penetrations that you're testing them in the horizontal orientation as though they were penetrating a ceiling or a floor. What else would we test in here? We do submersion tests in here, like fiber reinforced plastic gratings that are used for the offshore oil industry, and other specimens like that have to be submerged in a furnace atmosphere, completely immersed. We will cover the top with just blanks, steel plates, insulated steel plates, just to hold the temperature inside the furnace, and we'll run gratings and different types of materials inside the furnace. So, Dave, if you want to try to get a shot in there, there's not much light, but what you'll see, hopefully along the bottom, is holes, which are the burners, and then you see cylindrical sleeves, which are riser sleeves. Those attach to our exhaust system, which is built into the floor of the furnace. So by having riser sleeves, it forces the air to go up to the top surface of the furnace before it's then pulled back down through the floor. So we know that we're not just getting stagnant air near the top, and there's a lot of air exchange going down at the bottom. And then along the top edge, you saw the furnace thermocouples, like you did the probes coming through the back face of the furnace. And the last furnace is nearly identical to the large horizontal, except it's, a miniature. This is our small horizontal. The large horizontal had a top opening of 12 foot by 16 foot. This is our smaller one. This is 4 foot by 4 foot. It's good basically it's good for smaller samples that we don't need such a large furnace for. It provides savings to our clients to run a cheaper test and still get what they need. So that's basically our furnaces, unless you have any other questions about them, Dave.
No, I think that's it. Do you want to go straight to that?
Yeah. So the other apparatus that we have in our large-scale furnace facility, this is our multi-story apparatus. The tests that are run on this apparatus are the NFPA285 test and the Astm E119, at least currently. There's more standards that are in development currently. NFPA285 is the most common and the biggest one. If you want to get a shot of this dense glass wall, there's nothing proprietary about it. So this is a test assembly that, this is the base substrate of a test assembly that you would see used on the multi-story apparatus. So I'll explain the test really quickly. The whole purpose of this test is to test exterior curtain walls for buildings. Now, a curtain wall is a non-load bearing construction. It's the facade. It's what's on the very exterior of the building. And what you find in construction today is a lot of exterior facades that want to add insulation value to the building. So they're typically insulation materials are combustible. So this evaluates the ability of a curtain wall assembly to resist the spread of flame either vertically or laterally during a half-hour test. So the way this test starts is you have the bottom room, and this is a natural gas burner. It basically just flow natural gas straight through this pipe right here. So for the first 5 minutes of this test, just this burner is going. And you think again, this is a test assembly. So when this test assembly is put up against that apparatus, the whole second floor is closed off because there's no openings in it, you know? It's held tight against the face of the apparatus. So the first floor has a window in it, so that allows heat to escape and start to impinge on the area above the window opening that's built into this first floor. So for the first 5 minutes of the test, we have that window burner, that room burner going. We call it the room burner. 5 minutes into the test, this is actually another pipe burner right here that has natural gas going to it, and it's got a slit cut in the top of it, and we start that burner. And at 5 minutes, it's rolled up to the assembly, and it sits right below the top edge of that window, the window header. So now you have a gas burner going inside the room and a gas burner going at the window header. And what that's supposed to represent is flashover in the room occurring. The room has been completely consumed by flame, and now that flame is looking for any oxygen it can find. The window in an actual building breaks out, and that flame goes flying out the window, consuming any oxygen it can, and it winds up impinging on the wall directly above that window. And that's where this test really begins. So that's 5 minutes into the test. That condition continues for another 25 minutes in the test, and every 5 minutes we up the gas flow based on predetermined calibration rates. We're supposed to hit specific temperatures on the outside of the wall and specific heat fluxes on the outside of the wall. And basically the failure criteria is if flame is able to propagate over the exterior surface or through the core of the assembly 10 feet up above that window, or what would be 1 story in an actual building. We're looking to compartmentalize the fire and prevent it from spreading from one area on fire to another. Also, lateral flame spread, as a failure criteria, it can't spread 5 feet to either side of the window, but you know, flame tends to travel upwards, so you don't see that very commonly. The typical mode of failure would be straight up the wall on the exterior face. So yeah, that kind of covers this apparatus. Anything else?
No, I think that's it. Dave, thanks a million.
Absolutely.
Okay.